Hey everyone. So, Pokhara University's MWC exam. Feeling the pressure? Yeah, I get it. If you are, then you have come to exactly the right place. We all know there's just a mountain of stuff to get through.
I mean, you look at these past papers and it's a little overwhelming, Haina. But what if I told you there's a secret pattern here? That the most important questions, they just keep showing up again and again. Well, guess what? We've done the hard work. We've analyzed all the papers and we've found that pattern. And today, we're going to break down the 5 most repeated questions so you can study smart, not just hard.
All right, so here's our game plan. Think of this as the greatest hits album for the MWC exam. We're going to cover the evolution from 1G all the way to 5G. Then we'll solve that hexagonal cell mystery. We'll peek inside the GSM architecture, figure out how everyone shares the air, and finally, we'll break down the blueprint for 4G, which is LTE. So, you ready? Lo, suru karum.
Okay, first on our list, the evolution of mobile tech. You know, this topic is basically the foundation of the entire subject. And honestly, a question about it is pretty much guaranteed to pop up. You'll often see it right there at the beginning of the exam paper.
And hey, don't just take my word for it. Here in ESTA, the proof is right here. Just look at this question from a recent paper. It literally says, list down the salient features of cellular technology from 1G to 5G. I mean, they couldn't be more direct. So knowing this stuff isn't just, good background theory. It's a direct way to score some easy marks.
So the beauty of this is how simple it really is when you break it down. Think about it. 1G, that was just analog voice, plain and simple. Then 2G came along with GSM and boom, we got digital voice and texting. 3G was the game changer that brought us mobile data. 4G with LTE, that's when we got true high-speed data and video streaming. And now, 5G is all about the Internet of Things and that crazy fast, ultra-low latency. See? Each generation has that one key thing that defines it. That's the main takeaway here. Got it? Bujnu Bayoni?
All right, let's jump into our second greatest hit. And this one is a real favorite with the examiners. We're talking about the fundamental geometry of cellular networks, why they look the way they do. And yep, you guessed it, here's the proof, right from a fall 2023 paper. It's almost always a 2-part question. First part, why hexagons? And the second part is that classic proof. Prove Q equals the square root of 3n. But don't let the math scare you. This isn't just some boring problem. Let's frame it as a little mystery that we're going to solve together, right now.
So, why the hexagon? What's so special about it? Well, the answer is actually pretty simple. It's because hexagons are the perfect shape for tiling a surface. They fit together without any gaps, kind of like a honeycomb in a beehive. This means you get the most possible coverage area with the least amount of overlap. In other words, it's just the most efficient shape for the job, period.
Okay, you ready for the proof? Lao, let's do this. Step 1 is all about understanding the geometry. So we have this letter N, which stands for the cluster size. That's just the number of cells in a group before you have to start repeating the frequencies. And you calculate N with this formula using 2 integers, I and j. It's simply N equals I squared plus j squared plus I times j.
Okay, on to step 2. Now we bring in the distance, d. This is the distance between the centers of 2 cells that are using the exact same frequencies. We call them co-channel cells. And there's a crucial relationship here. This distance d is connected to the cell's radius, r, by this formula. d equals r times the square root of 3n. And now for the grand finale, step 3. We have something called the co-channel reuse ratio, which we call Q. And Q is just d divided by r. So all you have to do is take that formula for d from the last step and plug it in. What happens? The r's cancel each other out, and you are left with Q equals the square root of 3n. And that's it. Katham! Mystery solved. See, the whole thing just boils down to knowing that relationship between d, r, and n.
All right, moving on to our third greatest hit. Now we're going to dive deep into the most successful 2G standard ever, GSM. And let me tell you, understanding its architecture is absolutely non-negotiable if you want to pass this exam.
And here we go. Check out this question from a fall 2024 paper. Question 6a, asking you to explain the GSM system architecture. But here's the key part. Notice it says, with necessary diagram. That's not just a suggestion. That diagram is pretty much compulsory. You have to know it.
Just in case you think that was a fluke, here it is again in fall 2021. This question shows up constantly. It's a certified classic. Seriously, if you only have time to memorize one diagram for this entire exam, make it this one, the GSM architecture.
So what are the building blocks here?
Well, you've got the mobile station. That's just your phone. It talks to the base station subsystem, which then connects to the big brain, the network switching subsystem. But the part that trips a lot of people up are those two key databases, the HLR and the VLR. So let's clear up that confusion right now.
Okay, the Home Location Register, or HLR. The easiest way to think about this is that it's the permanent home record for your SIM card. It's the master database. It knows everything about you, your subscriber info, what services you've paid for, and your last known location. It's the one central file cabinet for your account.
Now, the Visitor Location Register, or VLR, is the opposite. It's temporary. So imagine you travel to a different city. The local network there needs to know who you are, right? So the VLR in that area creates a temporary file for you by borrowing your info from your permanent HLR. It's like getting a temporary library card or a visitor's pass for your phone, and it's only good while you're in that specific area. Okay, on to topic number 4. Think about this. We have a very limited amount of radio spectrum, but millions and millions of users who all want to talk and use data at the same time. So how on earth does that work without it all turning into a garbled mess? The answer, my friends, is multiple access.
And you better believe the exam is going to ask about this. Of course it will. Here's a question from a recent paper asking you to explain the big three: FDMA, TDMA, and CDMA. Knowing the difference between these is absolutely crucial. And this breaks it down perfectly. Let's start with FDMA, or Frequency Division Multiple Access. This one's easy. Everyone gets their own private frequency slice. It's just like how different radio stations each have their own frequency on the dial. Simple. Then you have TDMA, or Time Division Multiple Access. Here, everyone shares the same frequency, but they take turns using it. It's like being in a super fast conversation where each person gets a tiny time slot to speak before the next person goes.
But CDMA, now this is where things get really clever. With Code Division Multiple Access, everyone uses the same frequency at the same time. And you might be thinking, how is that possible? Well, the trick is that every single user is assigned a unique code. Your phone's signal is stamped with your code, and the receiver is listening only for that specific code. It's the perfect analogy. Imagine you're at a party where everyone is talking at once, but each person is speaking a different language. You can easily tune everyone else out and listen only to the person speaking your language. That's CDMA.
And here we are, our fifth and final key topic, LTE, which stands for long-term evolution. This is the 4G technology that really gave us the high-speed mobile internet we're used to today. And you can bet the exam loves to ask questions about its core design principles.
Case in point, Spring 2023 paper. The question is, explain in detail the design principles of LTE. Now notice what they're asking. There's no calculation here. This is a pure theory and concept question. They want to know why LTE was designed the way it was.
So, what are those principles? Well, this is basically your cheat sheet right here. First, LTE was built for super high spectral efficiency, using fancy tech like OFDM and MIMO to cram more data into the airwaves. Second, it was designed for really low latency, that's the delay, which is what makes apps feel so snappy. Third, it's an all-IP packet switch network. It also has a much more simplified network architecture than 3G did. And finally, it's super flexible with how it uses bandwidth and frequencies. Honestly, this slide right here, this is your answer to that question.
So there you go. That's it. Your ultimate MWC exam checklist. You need to master the evolution from 1G to 5G. You have to be able to write out that hexagonal cell proof in your sleep. You've got to know that GSM diagram, especially the roles of the HLR and VLR. You must be able to clearly explain the difference between FDMA, TDMA, and CDMA. And finally, you have to remember those core design principles of LTE.
Look, we've laid out the roadmap for you, and it's based on years and years of past papers. The pattern is undeniable. So now, the only question left is, which one of these 5 topics are you going to master first? All the best, and Ram Rari Exam Din Hola.